So it is time to get into Chapter 2, Lesson 3, where we talk about Newton's laws of motion. As you see on page 44, we are introduced to Sir Isaac Newton. Now, some people talk about how Sir Isaac Newton came up with the law of gravity by sitting underneath an apple tree. An apple fell on his head, and he began to think and wonder about gravity. Now, I don't know about the historical fact of that, if that's true or not, but that is what the legend is. But we do know that Sir Isaac Newton came up with three laws of motion, not just on gravity, but motion as. So let's begin by looking at Newton's first law of motion. Now there are two parts to it. There's an A and a B, basically, where we talk about the law of inertia. Now you might remember this from the introductory video that we had as we got into our forces and energy book. But when I talked about inertia, then we said that there are two parts, and the first part is that an object at rest will stay at rest unless a non-zero force is acted upon it. Now, as I said in our previous lesson, please don't let the non-zero term get you all confused. It simply means what the two words mean when they're separate from each other. Non is not, and zero is an absolute zero balance. There is no energy. So non-zero means there has to be something greater than zero, and then there's a force acted upon it, and then we'll start seeing some motion. So when we look at the example in the bottom left, we see a box just sitting there. That box will sit there for days, years, millennium, unless there's an energy that comes along and a force causes it to move. So we see the individual, he's going to apply his force to it, and the box indeed is going to move. Unless that force is acted upon it, then that box is just going to simply sit there. In the same way, then, we just look at it in reverse. Part B is an object in motion stays in motion unless a non-zero force is acted upon it. So if there's a force greater than zero, it can cause the action to no longer be happening. So the motion of the box sliding down in the bottom right example, then we see an individual coming along. She applies her force into the box and causes it to stop its motion. So when we're talking about the first law of motion, then we have this applied force, either to cause and change the motion into moving or stopping, or maybe even slowing down, maybe even changing a direction. But what we end up having is an unbalanced force because it's going to cause a change in the original object and the motion or lack of motion that it is currently showing. When we look at the law of inertia, then we need to understand what inertia means. And I kind of gave you the example when we first started talking about forces, right? The inertia is the resistance to change in a particular motion. When you're going to get on one of these sphere crazy people rides, right? Then you're strapped into the sphere and it's going to slingshot you with giant rubber bands up into the air, right? So I've never experienced it because I don't like being held down and restricted like that, and I definitely don't want to be thrown around like I'm part of a rubber ball. But some people enjoy this. But your initial takeoff is your body's at rest, the cage is at rest until they release you, and then all of a sudden it throws you. And then when you get to the very top extension of the giant rubber bands, then your face goes flying forward while the cage itself is pulling you backwards. So there's a constant battle between the going and falling and going and falling, and your body's going to bounce back and forth, back and forth, back and forth. Look how much fun they seem to be having. But this is a change of motion. That's what inertia is, right? The moment you get to the top, then you start going back down. All sorts of fun. In the same way, if you're riding a roller coaster, the same thing happens. Notice that the track is going straight forward. That's the motion that your body is going in. But the track changes. Well, as you and the car are traveling forward and the track suddenly pulls the car to the left, your body wants to continue to go forward. So you start slamming into the right side of the car or the unfortunate passenger sitting next to you, right? So as our body is changing the direction, the vehicle has to change direction as well, vice versa. As I first talked about inertia, you can be driving down the road, and then if your parents suddenly have to slam on the brakes, you end up flying forward. because your car is going at a certain speed, your body's going at the same speed, but then when that vehicle suddenly stops, your body still wants to go at that same speed. That's the benefit of wearing a seatbelt. It'll keep you hopefully safe, right? And if you don't believe that, then you can watch all sorts of videos on crash test dummies, and they show you what happens to your body if you are not wearing a seatbelt. Because of inertia, your body wants to continue to go, and you might go flying out the front windshield of your vehicle. When we look at how mass is going to impact the first law of motion, then, right? So hopefully it would make sense that if we have a greater mass, then the more force is going to be applied to get an object to move. So we have two different boulders here. We have one boulder that's 300 kilograms, and we have one that's 30 kilograms. If we talk about the inertia that's happening, the motion that's happening is basically static friction. They're not moving. But we have to break that static friction. We have to break that force with an energy in order to cause them to move. So it's going to take someone much bigger and stronger to move the boulder on the left than it does for the person to move the one on the right. Greater amount of energy or greater amount of force is required to change that inertia. When an object is moving and then hits something, then we have some major problems, right? So if it's going to hit something soft, it's not that big of a deal. However, if the faster the object is or the greater the mass is, because that's what we're looking at, then the more energy it's going to take. So if we think about Supergirl stopping a car, yeah, she might do some damage to the car, but it's not going to take as much energy as it will for Superman to stop the train. Bigger mass, bigger energy requires more energy to be applied for that inertia to take place. All right, so as we look at the second law of motion, then it deals with acceleration, and acceleration is the increase of force or the increase of output. Acceleration of an object depends on its mass and the amount of force that is being applied. So, how big is the object and how much energy is being used for it to accelerate or in order to move? So, when we look at acceleration, then we have this math equation that we could be able to do. Now, this is one of those lessons that we saw earlier on in chapter 1, but once again, we don't need to be able to necessarily calculate these because this is more of the middle school standards. But just to introduce it to you, when you take your final speed and you subtract your initial speed, so if you're measuring it from one point or one sign even on the road to the next one, then let's say you were at your final speed of 55 miles per hour. You started out at 35 miles per hour and it took you 10 seconds to get there. So we would have the 20 divided by 10, which would give us 2. So we're just trying to see how big that object is, though, compared to how much force is needed. So when I have force divided by mass, I can see how much force is needed. So when we have these little electrical cars, these little teeny tiny things that I don't want to be stuck in, then we have to look at how much force it takes to get that little itty bitty car to move. Now, the little itty bitty car doesn't take a lot of energy to move because it's lightweight and it's made to be lightweight, and the material that it's made out of is more compacted and less dense. However, when I look at a semi, that's going to take a lot more force, right? So when I push down on a little gas pedal or battery pedal, I guess for an electric car, I don't need to push it down very far to get that little itty bitty car to move. But in order to get that semi going, then you always hear them revving up and cramming their foot down on the gas pedal because it takes a lot of force to get that big mass to move. Now, acceleration is measured all over the world by scientists using the International Standard of Measurement, or the SI, of meters per second squared, which means meters per second per second. So when we're talking about force for acceleration, that's what we end up measuring. So meters per second per second. If I want to know how to figure out the force, then I have to take my kilograms, my mass of what the object is. Now, once again, that's going to be called by something else. We were introduced to Newtons earlier on in chapter 1, and that's what Newtons is when it comes to the force being able to be applied to get something to move. So if you think back to the dogs pushing on the box, we had so many newtons on one side, so many newtons on the other, or we had the compounded newtons on the left to get the box to move to the right. They're basically taking the mass of the object and multiplying it by, excuse me, the force of acceleration, which is meters per second squared. The third law of motion then is understanding what a balance is. So if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. So we basically make all of those fancy words that you learn more in like 8th and 9th grade into an easier way to remember. For every action, there's an equal and opposite reaction. If I push on you and you don't want to move, you have to push back with the same amount of force. If I push on the door and I don't turn the handle, then the door is going to push back with the same amount of force because it's not going to open. So for every action, there is an opposite and equal reaction. So when we talk about action-reaction pairs, we don't think about what's happening when we're walking, but there is an action versus reaction pairing happening. As you are stepping down onto the ground reacts by giving you a force of an equal amount in the opposite direction. Your energy is going down, and the energy from the ground is going back up. We know this because you're not sinking, and you're not being thrown into the air because the ground's not pushing back with a much greater force. So as long as you're able to push against the ground, then the ground can push against you in an equal and opposite reaction. This person leaning on the wall. Notice that the wall is indeed holding him up. His force is going into the wall, and the wall is given the exact same amount of force going back. We know that because he's not falling through the wall, and he's not having the wall falling on top of him. So we have an opposite and equal reaction happening. As you sit in your chair is designed to push back with the same amount of force. You're not flattening the chair down to the ground, and the chair is not throwing you up in the air as you sit down. So we have an opposite and equal reaction when we're sitting in our chairs. So the third law of motion from Sir Isaac Newton, he's telling us that for every action, there's an opposite and equal reaction. They're not canceling each other out, right? What they're doing is they're balancing each other. They're making it an equal balance so it doesn't appear that there's any motion happening. If we think back to the swimming example that we had in Unit 2 or Chapter 2 when it comes to friction, right? The water is not being canceled and the swimmer is not being canceled. There's a constant action and reaction happening as the swimmer is swimming towards the water. So the water's energy is going towards the swimmer and the swimmer is going towards the water. They're kicking with their feet, applying their action or force with their feet, and therefore the water is pushing back so that they have an energy to propel or move forward, right? So when we think about volleyball also, there's an opposite and equal reaction. You both jump up, you go to block it, and you hit it. If it's not an equal reaction versus action motion or pairing, then the ball is going to go more in one direction. If I hit it harder than you, it's going to go in the direction away from me. You hit it harder than me, then it's going to go in my direction. But if we hit it with the same amount of force right in the middle, then the ball ends up falling straight down. So we have an opposite action versus reaction when the same amount of force is being applied. Okay? So that's what the idea of balanced is. If you think back to the balanced scales, being able to equal everything out one for one. So it's not that there's 0 newtons, there's a certain number of newtons, both hands hitting the ball, and the ball is given the same amount of newtons back to the individuals. So here's a video to help you hopefully understand a little bit more about the 3 laws of motion. So after you do this, then your next class for science, if you will, then you should be doing your assignments to help you answer the questions.